118 for the sensitivity, and this is wideband. You drop down, gives you a noise floor of minus 122. You need 17 dB for the carrier to noise. That says you need a minus 105 dBm. Median signal level to give that audio quality. But now you're going to have to add margin to get the probability up. And in this case, you're going to add 13.2 dB to get a 95% probability of having that median signal level that you're looking for that will give you that audio quality. And then just, not for giggles, but because you need this in the real world, you need another 1 dB confidence factor that you will be able to have that. So in essence, you need to design for minus 90.8, in this particular case, to have a 95% probability with the DAQ3 on a wideband analog radio. Now, analog versus digital. Comparing the top two rows, you can see that the 6 dB tracks all the way through in the analog world. But if you compare it to a Project 25, P25, which is C4FM using the original IMDE vocoder, it required 7.6, but it's got a much narrower IF. IF's less than 6 kilohertz. But you'll notice that as you go up for the higher audio quality, you can do it with a whole lot less margin than you can with the analog. So the digital gets the audio quality better in a hurry. But there's the flip side of that, is that once you're down to the low signal levels, the human ear will allow you to understand what somebody's saying in the presence of fading and static, but the vocoder is going to mute on the digital system. So you have that cliff effect that will suddenly cause everything to stop. And here's just a comparison, and I've got to emphasize these are static values, and we're really using faded, but what I'm trying to show is the loss of the audio quality as you narrowband. The green line is the static SINAD versus the carrier noise ratio for a regular ±5 kilohertz deviation radio. The next one is blue with a 2.5 kilohertz or narrowband radio with a medium wide IF. Medium is the 8 kilohertz that I've been talking about. The red is what I would call a narrow IF. This is the same IF bandwidth that the digital radios would use, like 6 kilohertz. And you'll notice that the SINAD sensitivity changes a little bit, but those are usually offset by the bandwidth change. So, okay, there's kind of a wash in that general area, and again, you're not going to see a difference in spec sheets normally between an analog and a digital or a between a wideband analog and a narrowband analog. So you won't see a difference there, but when you start ratcheting up the signal to high signal levels, you'll find that the audio quality will degrade somewhat. So the maximum audio quality you can get is a function of the IF bandwidth that your radio is providing. Now this is from GSB 88.1, and this shows an example of loss of sensitivity due to adjacent channel for some different configurations. The document itself provides something on the order, I think it's like 23 spreadsheets now, that allow you to calculate any combination of modulation that's typically out there against any possible receiver model that we have identified. So in this particular case, on the left is a 6 kilohertz receiver against a, see, this is an analog. No, this is a P25 digital. So I can't read this screen. Here. Okay, so we're showing the same modulation, but we're moving the IF from a 6 kilohertz wide IF to a 10 kilohertz IF. And you can see that the value of the adjacent channel power ratio changes. And it changes rather dramatically from 70.8 down to 48. That's about a 25 dB difference just on the width of the IF. And the adjacent channel power, if you subtract the carrier to noise ratio from that, the static carrier to noise ratio, that gives you the adjacent channel rejection ratio. And so in a way, there's a section in GSB 88 in Annex H that says if you can take the adjacent channel rejection ratio and the other information that's in there, you can get a pretty darn good idea of how wide the IF is on a given receiver. Now these also curves. The spreadsheets do the upper two graphics, but the curves are also in the document. But the only thing we publish in the document itself are tables, because it's intended for people that are running computer programs to be able to do a lookup on the table. And it's a lot faster on computers to do lookup tables than it is to do calculations of complex numbers. So how do you estimate this loss of coverage? Well, if you're terrain limited, there's probably little loss due to the rapid increase of loss due to the terrain effect. So terrain limited, that's such as you suddenly drive into a forest, or you suddenly hit the crest of a hill and you go on the reverse slope of the hill, and there's a dramatic loss increase. And in those kind of cases, you probably see precious little difference between wide and narrow analog. However, if it's not terrain limited, if it's uniform terrain, then you can estimate based on the propagation model, assuming that all the other elements remain constant. And there's two ways to look at this. You can look at it as a probability of achieving the desired DAQ, but you're going to have a lower probability because of the narrowband, or a loss of DAQ over the whole coverage area. Does that make sense to everybody? Good. Testing for understanding here. Reduction in simulcast delay spread. There's a loss of sensitivity. And also in GSB 88, if you ever get a copy, and I highly recommend it, there's an annex in there that is devoted strictly to simulcast, although it's primarily aimed at digital simulcast. And I'll talk a little bit about why that is later. But it shows you the delay spread curves. A delay spread curve is delay going this way, carrier noise going this way, and you get kind of a hockey puck curve. And what happens is the delay goes up, you suddenly need more and more carrier to deliver a given audio quality. Well, you're going to shift that whole curve up. So it's going to affect the overall performance. The audio quality will change with simulcast because the delay spread curve has had to be moved up. It's more sensitive to level settings because you've reduced the deviation, so the tolerances you have to deal with are a little tighter.
That's not
I couldn't give you an affirmative answer or not, but it's intuitive that I think that's the case. So, trying to give an estimate, if we say there's a 3 dB loss